Hi, I'm Roger Dargaville. I'm a researcher here at the University of Melbourne's Energy Institute, and I'm going to be talking to you today about a modelling study we're doing called the Melbourne University Renewable Energy Integration Lab, or MERIAL. We're funded by the Australian Renewable Energy Agency, and it's a collaboration between the School of Earth Sciences, School of Engineering, and various entities such as GE, the Department of Treasury and Finance, and a group called Market Reform. So, one of the great questions we face in the energy sector is, what will the energy system of the future look like? We have lots of different technologies available to us, including the well-established renewable technologies such as hydro and wind, the emerging technologies such as PV, and more advanced technologies such as concentrating solar power. There are, of course, all the fossil fuel technologies we don't exclude in our modelling scenarios, such as coal and gas, ultra supercritical steam cycle, technology versions of those, and carbon capture and storage. There's also large-scale renewable power technologies that are dispatchable, such as geothermal and biomass. There's the issue of storage, chemical batteries, pumped hydro, and other forms of energy storage. Plus, on the demand side, there are lots of technologies such as electric vehicles and demand-side management and energy efficiency. So all of these different technologies have very different cost profiles and dispatch profiles. So some technologies are infinitely controllable by the operators of the systems. Some are completely at the whim of the environment, with solar PV, for example. So working out what the best combination of these different technologies is a real challenge. So the way we approach this is by using a computer model, which we've called MERIAL. So quickly, just about the two main technologies we're looking at the moment, which is wind power and solar PV. They're variable in space and time, and they're more or less out of the control of the operators. Wind as a technology is cheaper than solar PV, but the problem with wind is it's more or less random. You don't know from more than a few days in advance whether the wind will be blowing at one time or not. But it does run at a relatively high capacity factor of about 35%, or maybe a bit more in a good quality wind resource area. And it varies a lot over the country. So if you've got a large transmission system like we do in Australia, you can be more or less guaranteed that you'll have some power most of the time somewhere in the grid. Solar, on the other hand, it's much more predictable, but it's predictable in that you know for sure it's not going to operate at night. Unless you do have some storage integrated into that technology. It tends to be more expensive per unit installed, and it runs a lower capacity factor, the order of 15 to 20%. But the advantage of solar is that it works at very small scales, and so you can put it on a rooftop, and therefore it's competing with actual retail energy rates as opposed to the wholesale rates that wind competes with. So just between those two technologies, you can see that the comparison is very complicated, and you can't say straight out that one is better than the other. This diagram shows approximately how the model works. At the top there we have our weather model that gives us all our information about wind and solar radiation and temperature, which we use to predict demand. We do a selection of sites within the Australian domain, and then we allocate a certain amount of wind and solar technologies to each grid point throughout the model, and we simulate how that energy system would evolve. We use conventional dispatchable power to meet demand, and we run it through a transmission constraint to make sure that we don't have too much power generation in one part of the grid which isn't able to be transmitted into other parts of the grid where it's used. We then cost the whole system, looking at the operation costs, the capital costs, carbon price, and any missed supply that might occur. We then run through this loop tens of thousands of times, maybe hundreds of thousands of times, to find the least cost combination. So we use the computer to do lots and lots of different combinations to find out what that least cost combination is. We have a range of input data that we put into the model for the different technologies, and on this table you can see the costs that we use for brown coal, black coal, combined cycle gas turbines, open cycle gas turbines, wind, solar PV, and hydro. We also assume certain prices for gas and coal and what the carbon price will be. This is an example of a snapshot of 15 days of model output for January and July 2010. So we're using a hindcast using 2010 meteorological data. And what you can see in this particular scenario, where we have $120 a tonne as the carbon price, is that at that price, wind is the optimal technology, and it dominates the landscape. We have quite a lot of gas-fired backup, which provides power when the wind can't meet demand, and there's a little bit of black and brown coal still in the mix there at that price. The distribution through the grid, you can see on the right there, is reasonably uniform. There's a bias towards the coastal sites, which is of course what you'd expect being the windier sites. But what the model has tried to do is spread out your wind resources as much as possible throughout the grid to maximise that spatial variability and minimise the total system variability from your wind power. If we look at that same cost scenario but with different carbon prices out to a carbon price of about $200, you can see that at current carbon prices of $20 or realistically zero in the near future, wind only plays a very small part. At about $80 a tonne, we see that wind power becomes cheaper than fossil fuel, and that we see a very rapid ramp up between $80 and $120 a tonne. But from there on, we don't see very much change. The system is quite insensitive to further increases in the carbon price, which suggests that beyond $200 a tonne, you would need very high carbon prices to actually suppress gas as being the technology to provide backup. If we look at the carbon emissions with time, you see that the brown coal is pushed out of the system very quickly at the start with a relatively modern carbon price. The black coal stays in until about $100 a tonne, and we see a reasonably constant amount of gas in the system throughout the scenarios, providing balancing power for the system. In terms of cost, we see an annualised cost at the moment of about $15 billion a year, going up to about $27 or $8 billion a year at a high renewable energy system. So it's an approximate doubling of the cost of producing electricity. The second scenario I'd like to talk about is one where we look at what would happen if PV was very cheap. And we're running a scenario where we assume that solar is only 50 cents a watt, half a dollar a watt, which is less than half the price of what it currently is. But it's possible that it could happen in the future. In this scenario, at $120 a tonne, solar is a very large component of the energy system, but we actually see that wind is still also a very significant component in the energy system. We also see that storage becomes a really important technology in this scenario, because when you have a lot of solar, you need a lot of wind as well to provide power when the sun's not shining, and with that excess supply of wind, you save the system money by storing the excess power in pumped hydro storage when you can. As we saw before, the model likes to smooth out the distribution of the power stations throughout the grid wherever it can put them. Again, if we look at the time series of these plots, because we've made solar very cheap, it actually is cost competitive at zero carbon price. And so we see right from the very start of the scenarios the order of 20 gigawatts of PV being installed. And that actually doesn't change as the carbon price increases, because the PV is so cheap. It doesn't need a carbon price to be supported. The limiting factor is that you can't install more PV than what you have, because it doesn't provide power during the day, and so isn't that useful for meeting demand at all times of the day. The model, as the carbon price increases, phases out fossil fuel in favour of wind power, and the advantage of wind power is that it does blow at night as well as during the day, and so provides power to meet demand in those dark times of the day. The emission scenario looks very similar to the previous one, with brown coal being pushed out first as it's a higher carbon emitting technology, followed by black coal, with a reasonably constant amount of gas providing a load balance technology in the system. So as we said before, we see an increase in the cost of the energy system from current about $15 billion. It's a bit cheaper in this case because we've made solar so cheap that it actually reduces the overall cost of the system compared to what we currently have. And because solar is so cheap in this system, we see a cheaper system of about $23 billion per year when we get to a $200 a tonne carbon price. So to summarise, the optimal energy system will be a mix of many technologies. There is no one silver bullet that will provide a solution to meet all our demand needs. But the result is very sensitive to the cost of the different technologies. And if one technology becomes a dominant technology and through scales of economy it becomes very cheap, then that will give that technology an advantage over others and will tend to make it dominate. A really key result is that we see it's going to be very expensive to go to 100% renewables, that even at $200 a tonne we still tend to have about 15-20% of fossil fuel generation in the mix. So what I would expect to see in the system was that we would go to about an 80% emission reduction in the electricity energy sector, and that we would get further emission reductions in other sectors of the economy such as transport, agriculture and in industry sector. So thank you for your attention.